Hi, my name is Soumya Sudhakar, and today I'll be talking about my paper on balancing actuation and computing energy in motion planning. This work is done in collaboration with my advisors, Sertac and Vivienne. There's been interest in developing robotic platforms that are either very tiny in size, such as the RoboFly, which it weighs in at 100 milligrams, as well as robotic platforms that can go in very long duration missions, such as a sea glider, which can go on missions of up to 200 days in length. Both these characteristics mean that these robotic platforms are extremely power constrained. Applications for low power robotics are numerous, and they can solve problems such as inspections and exploration in hard to reach areas, persistent monitoring of the environment, novel ways of delivering medicine, and space exploration. And there's been many recent advances in low power robotic platforms, such as some of the examples here, some of which are insect inspired, and others such as the mini autonomous blimp. However, there hasn't been as much attention paid to how do we scale autonomy at this low power regime. In this plot, I've arranged on top the low power robotic platforms in increasing order of the energy they take to move 1 more meter. On the bottom, I've arranged various embedded computing platforms in order of increasing energy per second they take to compute. As you can see, in this low power robotic regime, the energy to compute is no longer negligible. In fact, the actuation energy and the computing energy are on a similar magnitude in many cases. When we look at motion planning, typically we would only want to minimize the energy to move along the path, or the actuation energy, as given by the equation on the right. Looking at the plot, the x-axis is the number of nodes in a PRM star, and the y-axis is the energy. And I compiled this simulating a vehicle that travels 1 meter per second on 1 joule and ran this on an embedded CPU. So when we only are looking at actuation energy, to minimize the energy function, we simply have to compute the maximum number of nodes since actuation energy is monotonically decreasing. However, when I plot the computing energy it took to compute all those nodes in the PRM star, you see what I mean, that the computing energy is no longer negligible. In fact, when you look at the total cost, which is the energy to move along the path, the actuation energy, plus the energy to compute the path, the computing energy, which is the purple curve in the plot now, you see that minimizing total energy is definitely not computing the maximum number of nodes, but rather stopping computing earlier at the red marker. And we see this in the equation as well, where I've added now a new term for the energy to compute the path. Now we'll assume that the actuation power, vehicle speed, computing power, and processing speed are all constant. And then we arrive at this equation where we have control over the number of nodes in order to minimize total energy. So you can see this has become an early stopping problem where we can decide how many nodes to compute before stopping in order to minimize total energy and arrive at the red marker of the total energy curve. Just note though that since we're having computing energy as part of the performance metric, any computing energy we spend as overhead to decide which number of nodes to stop at is also part of your performance metric. So it becomes a very interesting problem where your overhead is directly part of the performance metric you use to evaluate your algorithm. We propose computing energy included motion planning, or CEIMP. CEIMP works as an add-on to any anytime sampling-based motion planner. And the way it works is that the motion planner will sample a batch of nodes, and it will search for the best feasible path. It will give that information to CEIMP, which then decides whether to continue computing another batch of nodes or to stop computing and return the current best solution. Looking deeper into what goes into CEIMP, you see that CEIMP decides whether to stop or continue by estimating the future computing costs of continuing to compute another batch of nodes and estimating future actuation energy savings from computing another batch of nodes. Now, the computing model and model for predicting actuation energy savings from local optimization are relatively simple, and we're going to focus instead on the harder challenge of predicting expected actuation energy saved from a homotopic class change that could happen in the future if we sample another batch of nodes. So in this example, we have an environment where the obstacles are in gray, and we have a toy example of a PRM star motion planner. It's sampled a batch of nodes, and it's returned to us the best feasible path, which is in bold. CEIMP takes that information, and to predict the actuation energy saved, it needs to consider potential actuation energy saved from a homotopic class change in the future. And we can intuitively think of a homotopic class change as if the path cannot be warped into the other path because there are obstacles in the way. This is pretty hard to predict since it depends completely on the connectivity of the environment, which we don't want to spend so much overhead measuring this that we introduce too much overhead and negate any savings. The way we solve this is that we construct an occluded graph. An occluded graph is the same thing as the underlying motion planner's sampling-based graph, except instead of throwing away infeasible edges that are in collision with the obstacle space, we're going to hold on to them and keep track of them, in the hope that this is a way to probe the environment for potential homotopic classes that we narrowly missed, but we may later be able to repair if we continue computing. And you can also think of this as a way to predict, help us predict connectivity of the environment without spending computing energy to lay down more nodes. What we want to do is for each infeasible edge, we want to predict whether that edge really can be repaired in the future, and that it really does have an underlying homotopic class that goes through that neighborhood, or whether no matter how much we sample, we will not be able to repair it. So what we do here is that we model computing another batch of nodes as a measurement on the connectivity, and that measurement can return two readings, repaired or unrepaired. For example, edge A is a edge that can never ever be repaired in that neighborhood since there's no feasible path from the edge start to the edge destination. Meanwhile, edge B is an edge that if we sample more in that neighborhood, we most likely would be able to repair the edge and find a feasible path from edge start to edge goal. And we want to predict which edges are which through these measurements. Now that we've gotten a measurement by computing another batch, we run a Bayes filter on each infeasible edge in this occluded graph, which gives us a way to estimate whether that edge represents an edge that can be repaired in the future or an edge that can never be repaired in the future. And now that we have a stochastic graph, we run what we call an expected A star, which is a variant of A star, except instead of returning the minimum length path, it returns the minimum expected path length. From that, we have a homotopic class change prediction on path length. We can calculate future actuation energy saved, and CEIMP can decide whether to stop or continue. In these plots, the x-axis is the number of nodes in the PRM star, and y-axis is the energy. The red marker is the true minimum of the total energy curve, and the yellow marker is where CEIMP decides to stop. We can see that CEIMP does very well at stopping earlier than the baseline, which is the purple marker, and the maximum number of nodes to compute. And as a result, saves a lot of energy by doing so. On the right, we see an example where CEIMP stopped a little too early because it missed savings from homotopic class changes as seen from that jump in total energy. Still, it makes remarkable savings compared to the baseline. In practice, what this means is that CEIMP is accepting a longer path than what is computed by the baseline in return for not having to spend so much computing energy to find that shorter path. In this plot, as you go from the left to the right, the energy to compute becomes more expensive relative to the energy to move. On the y-axis is the total energy. The purple line is our baseline, which is 20,000 nodes being computed as the maximum number of nodes. This red line is our oracle without overhead. This is the true minimum of the total energy curve, given that we introduced no overhead. So we introduced no overhead to make a decision when to stop, so this is a theoretical lower limit. The orange line is the oracle with overhead, so it's the minimum of the total energy curve, given that we introduced some overhead. And the green line is a total energy with CEIMP. And we can see that CEIMP performs very close to the theoretical lower limit given by the oracle. And as you go from left to right and energy to compute becomes more expensive relative to the energy to move, CEIMP will make even more savings compared to the baseline. So, key takeaways. One, when we're in this low power robotics regime, it's worth not always thinking too hard. For example, a longer path we have right now might actually be lower cost in total energy than a shorter path that we have to compute a really long time for. Second, modeling computing as a noisy sensor helped us solve this problem and helped us give us a way to predict future actuation energy savings through this Bayesian inference formulation. Finally, inferring from failure allowed us to keep infeasible edges and run inference on whether they may open up in the future. And CEIMP updates its beliefs based on not being able to repair edges. And this whole process helped us efficiently predict future path lengths. And with that, thank you very much.